Hello everyone. I am glad to present the keynote talk which is focusing on emerging technologies for desalination and atmospheric water harvesting. Globally, water and energy are interdependent challenges that progressively threaten the survival of both human beings and animals. Owing to the rapid growth of population, industrialization, farm mechanization, intensive use of unsustainable technologies, and overexploitation of natural reserves, water scarcity is a natural realistic phenomenon thus far, impacting every continent seasonally. However, human involvement exacerbated its amplification and persistently formulated it into a chronic situation. Figure 1 shows the spatial distribution of regions affected by water scarcity. Natural hydrological or desalination cycle comprising of evaporation, condensation, and precipitation is not sufficient to meet the global thirst. Currently, 3.6 billion people have no access to fresh water, and projected to mount up to 5.7 billion by the end of the 2050. Approximately 2,800 billion cubic meters of water deficit is recorded annually. Figure 2 shows the projected supply-demand gap of fresh water that could be managed by artificial desalination due to availability of surplus quant of seawater. Artificial desalination is defined as separating salt and water from the concentrated brine mixture, or seawater. It is an alternative solution to extract the water beyond the natural water desalination cycle. Various desalination strategies have been patented, documented, and penetrated in water markets, aiming for removing the excessive salts from the amplest quant of seawater. More than 20,000 desalination facilities are being installed globally. Figure 1a elucidated the spatial distribution of scientific publications documented on desalination, whereas Figure 1b presents the worldwide geographical distribution of installed desalination localities. It can analyze that more than 50% of the desalination plants are owned by high-income countries and Gulf Cooperation Council countries. Generally, desalination technologies have been discretized into thermal and non-thermal engineering systems. In thermal systems, core concepts like evaporations and condensation are employed, whereas in non-thermal, filtration and crystallization conceptions have been widely investigated. Figure 2 depicts the classification of thermal and non-thermal desalination systems. Commercially, multi-effect desalination, multi-stage flash desalination, and reverse osmosis desalination technologies are actively employed by the desalination markets. Multi-stage flash and multi-effect desalination are thermally driven technologies require a significant primary heating source to undergo the separation phenomenon, whereas the reverse osmosis requires osmotic pressure that can be generated by utilizing the electrical energy. Today, reverse osmosis hold the market share of 70%, whereas multi-effect and multi-stage flash desalination contribution is only 18% and 7%, respectively. However, these commercialized desalination technologies are equipped with severe system discrepancies and environmental impacts. For instance, at system level, thermally driven desalination technologies faces corrosion of major components, scale formation, extensive energy consumption which lead towards the high desalination cost. Figure 1a shows the erosion in thermal desalination plants, and Figure 1b and Figure 1c shows the saline scaling formation. On the other hand, in case of reverse osmosis, low water recovery ratio ranges between 45% to 55%. Expensive membranes entail with low cycle stability, and exploitation of electrical energy are the potential threats. At environmental level, these commercialized desalination technologies produces aquatic discrepancies by increasing the sea organism's mortality rate, greenhouse gas emissions, and concentrated brine discharge. Figure 2 shows the current status, system discrepancies, and environmental impacts of commercialized desalination technologies. Therefore, low-cost, sustainable, energy-efficient desalination technology is principally required for addressing freshwater challenges or seasonal water scarcity. Emerging desalination technologies are remarkably designed to overcome the engineering shortfalls and for abating the environmental impacts in order to achieve the United Nations 2030 Sustainable Development Goals. In this regard, adsorption desalination is worthy to mention. The reason is that adsorption desalination technology possess capability to drive with the low-grade waste heat emitting from industries, steam turbines, engines, and even from automobiles' exhaust, thereby upscaling its contribution in reduction of fossil fuels dependency, global warming, and additional CO2 emissions for desalination. On system scale, the technology comprising of no moving parts and perform vacuum evaporation, consequently resolving fouling and corrosion issues as exist in the other commercialized desalination technologies. Above all, the cogenerating feature of adsorption desalination technology, such as producing fresh water along with high-grade cooling, addressing not even the water scarcity problem but also confronting the mounting air conditioning requirements. Figure 1 shows the thermodynamic processes employed by the thermal compressor to accomplish a single desalination cycle, which include adsorption, isosteric heating, desorption, and isosteric cooling in sequence. Figure 2 shows the schematic presentation of two-bed adsorption desalination system. The adsorption desalination system is comprising of evaporator, adsorption and desorption beds, condenser, and heating, cooling baths to produce prerequisite thermal fronts. The evaporator evaporates the water molecules which has been adsorbed by the adsorption bed. Once the saturation arrives, the bed pressure increases, an equivalent to condenser, and pressure during isosteric heating. After that, the desorption process taking place by supplying heat from the external source. The desorbed vapors subjected to condenser, where the condensate is collected as fresh water. To start the next cycle, isosteric cooling is provided for lowering the bed pressure and become equivalent to evaporator. This is a pilot-scale 4-bed adsorption desalination plant installed in National University of Singapore. This is a pilot-scale 4-bed adsorption desalination cooling system. In this study, a numerical model is developed in order to explore the specific daily water production University of specific cooling technology that possibly obtained from the adsorption desalination cooling system. The numerical model employed the thermodynamic heat and mass balance correlations, adsorption equilibrium profiles, in order to explore the performance efficacy. 5 variants of silica gel are tested, which include AA++ type, A5BW type, NS10 type, RD2060 type, and RD type adsorbents. It has been realized that AA++ type silica gel water pair outperformed as compared to other studied variants. The specific daily water production of AA++ type silica gel water pair found 15.5 cubic meter per ton per day at regeneration temperature of 80 degrees centigrade, while specific cooling power observed 38 megajoule per day. However, as the regeneration temperature drops to 50 degrees centigrade, the specific daily water production observed 12 cubic meter per ton per day, whereas the specific cooling power identified 28 megajoule per day, respectively. To conclude, AA++ type silica gel water pair is more efficient, followed by RD type, RD2060 type, A5BW type, and NS10 type silica gel adsorbent water pairs. Atmospheric water harvesting is another emerging solution for water-stressed countries located in arid and semi-arid regions, overcoming the challenges of long-distance delivery or transport of freshwater in arid regions. Our atmosphere contains 12,900 cubic kilometers of water vapor, that is 6 times the total volume of rivers present worldwide. Due to climate change from 1997 to 2016, average global atmospheric water content increased by nearly 3 grams per kilogram. This figure tells us about atmospheric water harvesting potential in liter per day per square meter throughout the globe. Red dots represent millions of people which have not access for safely managed drinking water in respective regions. Different atmospheric water harvesting technologies which are used worldwide. These include fog water harvesting technology, dew harvesting technology, vapor compression or direct cooling-based technology, thermoelectric cooling-based technology, and underground condensation technology. Although these technologies are being used worldwide for atmospheric water harvesting, but there are some limitations of such technologies. Like in case of fog harvesting technology, it is only applicable in regions having consistent presence of fog. Dew harvesting technology require high energy and not feasible in high temperature regions. Vapor compression or direct cooling based technology also require high energy for its operation and high unit production cost. Stop its usage. Thermoelectric cooling technology consume high energy, low water yield in water harvesting process. Here is strong dependent on the accessibility of electricity that is available only in certain locations. Underground condensation technology is limited because of high energy consumption and low water yield. Thanking to the adsorption-based atmospheric water harvesting technology, which can be conventionally utilized in arid areas, which suffer from an imminent shortage of water and lack accessing electricity. An adsorption-based atmospheric water harvesting technology, an adsorbent is a heart for its working and operation. An adsorbent is a material which adsorbs water vapors present in the atmospheric air, owing to its hygroscopic and hydrophobic nature. Numerous adsorbent materials have been developed so far, but the optimum adsorbent is one which harvests water from atmosphere at low relative humidity, have maximum adsorption capacity, and have high stability to perform multiple cycles. The beauty of such system is it could be applicable in dry and desert regions having low relative humidity, and can be operated with renewable energy sources including solar, wind, and low-grade biomass. This schematic shows working principle of adsorption-based atmospheric water harvesting. Initially, the adsorbent is exposed to ambient conditions to adsorb the water vapors, which is usually done during night. After adsorption, the system is covered, and the adsorbent is heated, which is usually done during day, allowing the system to receive natural solar radiations, and due to increase in temperature, hydrophilicity of the adsorbent decreases. Thereby, desorption of water vapors take place. The closed system's partial pressure slightly increases due to water vapor desorption. Finally, water vapors develop in condenser, as a result of heat exchange with source at a temperature below the system's dew point. Once the droplets have grown enough, gravity pulls them out of the condenser and directed towards collection tank. These are some laboratory-scale models of adsorption-based atmospheric water harvesting systems with their essential components. The first one is portable, which can carry at desired place. The second one is solar concentrator or focus type systems, which help to increase temperature of adsorbent bed for quick regeneration. Third and fourth are an example of renewable energy-operated adsorption-based atmospheric water harvesting system. This system performs multiple adsorption and desorption cycles for generating large quantity of water. These are some outputs of efforts made by researchers worldwide. Left figure is about potential adsorbents used for adsorption-based atmospheric water harvesting, operating at different relative humidity conditions. Among conventional adsorbents like silica gel and zeolites, metal organic frameworks have performed well from perspectives of high adsorption uptake, feasible in low relative humidity regions as well, and high stability of performing multiple cycles. Right side figure are experiments results of developed laboratory-scale adsorption-based atmospheric water harvesting systems in different part of the world. It can be observed that about 12 liter per kilogram of adsorbent per square meter is the maximum yield of water harvesting by experimental system, which can fulfill 3 to 4 person family drinking demand. So further improvement in such systems can enhance water production yield. Thank you.